So yeah, welcome Elizabeth Galloway. We're going to talk about stakeholder-driven impact-based forecasting framework for tropical cyclones. So a bit of a step change here. Thank you.
Hi everyone, I'm Lizzie. I'm a research fellow in environmental intelligence here. But I'm actually going to talk today about some work I did as part of my PhD, which was all about kind of impact-based forecasting for cyclone impacts. But I'm actually going to talk about how I kind of applied machine learning techniques to think about the kind of different stakeholders of impact-based forecasting and how you can kind of create a flexible, iterative framework to try and improve a model in a way that's responding to the current challenges in this area. So just to circle back, impact-based forecasting tries to answer the question, what will the weather do in terms of its impacts, rather than what will the weather be like traditional weather forecasts do. And answering this question allows us to disseminate early warnings. It allows us to explore alternative scenarios, like how might impacts change under climate change. And it allows us to understand some of the dynamics in disaster impacts, so how impacts relate to hazards and other conditions. But some of these dynamics are complex and non-linear, and that means that machine learning is a really good tool to apply to this. And one of the ways you can do this is by taking historical impact data and using machine learning models to kind of understand and try and pick apart some of those dynamics in creating impacts. And this is really great because it means we can move towards a kind of impact-based warning system rather than a kind of meteorology-based warning system that we've had historically. But doing this comes with a lot of challenges. So the kind of content, the way you communicate, the language you use in the warning is really important for how it's received. For example, if you disseminate warnings that there are going to be impacts, and then there aren't impacts, you get this kind of wolf effect, and you start to potentially lose trust in your warnings. On the flip side, if you have a warning that's too general, perhaps it's over too large a space, for example, you might also kind of lose the effectiveness of those warnings. And as I mentioned, we're talking about some complex dynamics here. The kind of historical impact data we're talking about also comes with a lot of uncertainty, so being able to communicate that in the warning is also really important. So all of this has kind of come together in a shift towards collaborative, people-centered design of warnings. But from a kind of data scientist, machine learning modeler's perspective, how does that actually look when we're trying to kind of bring in some of these challenges and consider them in our machine learning framework? So for my PhD research, I built an impact-based forecasting model. I used machine learning. I took a historical impact data set of province-level housing damage in the Philippines from tropical cyclones and a corresponding future data set, used an XGBoost model to predict province-level numbers of houses damaged. But I'm actually not really going to focus on that. I'm going to focus on some of my kind of model post-processing steps and how these are kind of aiming to respond to some of those challenges. So in the way that I've evaluated the model, questioned and kind of critically analysed the model's predictions, and tried to interpret those predictions in a way as to try and understand why the model is predicting what it's predicting. So I'm going to talk about three different approaches that I took to do this. The metrics I used to evaluate the model, the incorporation of uncertainty via quantile regression, and then trying to increase the interpretability of the model using SHAP feature importance analysis. So for evaluation metrics, I'm going to focus on using how I use the F1 score. So this is a score based on true and false, positives and negatives. And these are kind of concepts that are firstly quite well understood by people that are experts and non-experts. This means that makes that kind of communication part a bit easier. But the key part of F1 score for my application was that you can actually adapt them. So normally in kind of a machine learning classification application, you would look at kind of a binary, are you correct or incorrect in your prediction? And if we're asking about this boy who cried wolf effect, are we predicting whether there will be an impact or not an impact correctly, then using the F1 score in this binary way is useful. But what we can also do is we can ask how well the model is predicting impacts above and below certain thresholds. So we could use, for example, a threshold of 10,000 houses damaged and calculate an F1 score for that. That would be much more useful for a stakeholder who might be interested in whether the model can predict the most highly impacted provinces. So what does this look like in practice? Well, this is an example of my model's prediction for one particular cyclone on the left, And you can see, just kind of by comparing the two maps, that the model predicts the spatial pattern of the houses damaged in the provinces very well, but we can actually learn more if we look at those F1 scores. So I've calculated F1 scores for the 0 and non-zero scenario, but also for whether impacts were above and below 100 and 1,000 houses damaged. You can see that those F1 scores for the 0 and non-zero scenarios are quite significantly lower than those for the more highly impacted provinces. The reason for this essentially is that the model is predicting that there were impacts in lots of places where there actually weren't. So that's really kind of interesting for those who might be interested in the scenario of the Boyhuis-Wolf effect, whereas those who are interested in the high impact scenario would perhaps be looking to use this model, this particular output of the model, because it is able to replicate where those high impact provinces are. So secondly is uncertainty. So I've used quantile regression, which is essentially predicting what your prediction would be at a specific quantile of your choice of the distribution, rather than predicting the mean, as you normally would. So you can see here the actual prediction, the mean prediction is shown in the red dot, and your quantiles are shown in the black bars. Here I've shown a 90% prediction interval, so 95th and 5th quantile. But again, this provides the users flexibility over their choice of quantile and kind of how much uncertainty it is they want to be reflecting in their model output. And it also enables you to kind of place your prediction in the context of your training data. So what might an extreme impact look like based on the kind of historical cyclone impacts that we've seen. So again, what does this look like in practice? So you might ask, what does a kind of an extreme value of a particular cyclone look like in terms of its impact? And here you can see on the far right, the 90th quantile prediction is quite significantly higher than your actual observed and predicted housing damage. And it starts to give you an idea of what your kind of range of impacts you might be looking at. Finally, feature importance analysis. So I'm sure lots of you are aware, but SHAP analysis basically tells you how all of the features are being used by your model to make your predictions. So this is just a summary plot, where it essentially is ordering each of your features by mean absolute SHAP value, where your top feature listed here is your most important, essentially. So your minimum distance to the cyclone track is your most important for predicting how high your impact will be, which is unsurprising. But I'm actually going to talk about how you can use it to ask what features were used to make specific predictions. So a specific province's housing damage prediction for a specific cyclone. And you can ask exactly what the contribution of each feature was. So this particular example is showing the prediction error for one subtropical cyclone, where the red is an over-prediction and blue is an under-prediction. And for that circle province in the red, your feature importance shows that, so actually the cyclone track passed quite far to the south of this province, and so the minimum distance of the track is reducing your predicted housing damage. So that's shown in the blue arrow to the left. And most of your other features are increasing the prediction. This is giving you, despite your province being fairly far away from the cyclone track, we're still getting quite a significant over-prediction. That would make the blue province of the circle, you get a very significant under-prediction, but actually your feature importance is telling a different story. So although this province was a little bit closer to the cyclone track, your minimum distance from the south is still acting to reduce the predicted impact. So something a bit strange is going on here with the model. I can't necessarily explain it, but perhaps those with local expert knowledge who knew what exactly went on in these provinces during these cyclones could help you to understand and help model developers to understand that there might be features that are missing here that will help us to explain some of these differences in predicted impacts and help you essentially iteratively design the model so that you can improve it going forward. So just to summarise and kind of loop back to some of those challenges and how these different applications have addressed them, by evaluating the model with kind of all these different types of metrics, you can ask these questions like, how often would we get this Boyhuis-Wolf effect? So, for example, policymakers or those who disseminate the warnings would be interested in looking at metrics, different metrics with different thresholds. By including uncertainty, obviously this gives us a way to communicate uncertainty and also avoid these kind of overly general warnings by being able to place your prediction in terms of the context of historical impacts and historical cyclones, which is really important when you're trying to communicate how impactful an event might be. And finally, being able to interpret your model helps us kind of understand what it is the model's actually doing, to be able to improve the model and identify these kind of points of uncertainty where the model might be kind of failing, and so you can improve it with an iterative process by collaborating with local experts and model developers to improve the model predictions in the future. And that's all from me. Thanks.
That was brilliant. Thank you very much, Elizabeth. Any questions? Got time for a couple of short ones, maybe? Andy, do you want to come and set up? The one thing that I was really interested about actually with this is that I think you highlight something really important, is that when you're going to use these kind of models for real world applications, thinking about things like the boy who cried wolf, and actually the risk of putting into production models where you don't communicate uncertainty correctly, or you alarm people unnecessarily, could have significant implications. And do you have, one thing I've always found very difficult in pretty much every project I've ever worked on, is how you communicate the uncertainty. Because whilst I guess within this room, we're familiar with the concept and probably comfortable with uncertainty, but do you have any thoughts about how you can convey that, especially within an alarm system or alert system? Is there a way you think it can be done?
Yeah, so I think that's a really challenging thing to think about, and it probably depends on the type of thing you're warning and the kind of audience that you're aiming your warning towards. But a lot of the impact-based warnings that are kind of disseminated currently, or working towards currently, are done in a categorical way. Lots of kind of impact-based work is done categorically as well. I used a regression model, but actually did quite a lot of kind of evaluation metrics that looked at how well the impacts kind of fell within a certain order of magnitude. And I think communicating it in terms of a possible range, maybe in a kind of like hazard matrix, like a risk likelihood matrix, is something that's understood by a wider range of people. So probably translating something like a regression model output into more of like a red, amber, green risk matrix is something that would then kind of just kind of be recognisable to general public.
Thank you very much. We do have a couple of questions though.
I can probably project if you want.
Okay, yeah, go on then.
I thought the discussion about interpretability was quite interesting, particularly when you were just talking about uncertainty. And looking at your slides, I suddenly went, I wonder if there's an opportunity for those two to be associated or linked a lot more. And is that something you've looked into now that you're nodding, or exploring, or I don't know?
I did explore how you could essentially use a quantile regression output to inform where you did your feature importance analysis on the local level. So if you see huge uncertainty intervals, which you do in a lot of the really high impact provinces, you can then ask, well, why was that impact so huge according to my model, or why was it so under-predicted according to the model? So yeah, kind of the whole point of the process is that each part of it can inform the next part, and iterative to hopefully improve and respond to these kind of challenges. Yeah.
I think there was one very quick one.
I guess in your estimate of a variation, the error comes from not just your machine learning model, but the weather forecast itself. And I would like to know how you can entangle. Do you have any thought entangle these two errors?
Yeah, it's a really important thing to think about. So there's error, obviously error in the modelling, but also error and uncertainty in the impact data as well as the meteorological data. Plus, there's lots of other feature data sets that have gone into it, all of which have come with their own uncertainty. So all of those need to be taken into account, particularly if you're also thinking about using this in a forecasting sense, because particularly when you're kind of 5-10 days out from a cyclone forecast, the track's kind of error could be huge. So one way I kind of envisage this becoming more useful is if you had an ensemble of forecasts, actually applying this impact forecasting model to every single member of an ensemble, because actually once the model's trained, it's super fast. So being able to use all of the ensemble members to get kind of an uncertainty on your uncertainty in what your impacts might be would probably be a really good way of using it. And then as your forecast kind of tightens, as you get closer to the time that a cyclone might make landfall, you can then be hopefully slightly more certain on what your level of impacts will be. That's kind of where I see it being most useful.
Well, thank you again.